So in this lecture, we're going to look at some of the collective communication functions in MPI.jl. Collective communications in MPI or message passing interface refer to these types of operations kind of illustrated here: broadcast, scatter, gather, reduction. Where broadcast is an operation where you're going to take an item that's on one processor and distribute a copy of that item to all the processors. Scatter is an operation where you're going to take a group of items on one processor, partition it into individual parts that are usually equal to the number of processors, and then send each of those parts individually out to each of the processors for work to be done on them. Gather is kind of the opposite of scatter. So we're going to take individual pieces on individual processors and then group them together on a single processor. And then reduction is some type of operation. In this case, it's a summation operation done in parallel. So usually, in this case, you would have, this is a summation, so you'd have 1 and 3 are added together. At the same time, 5 and 7 are added together, and then those two's resulting sums are then added together to produce a reduction summation, or the total sum over all processors in this case. So we'll take a look at each of these individually with some examples in code. I think that's the best way to learn MPI here. So we'll start with scatter, and in this case, rank 0 acts as a leader. It's going to create a list, and then it's going to scatter out that list into uniform parts to all processors. So with all the code that you'll see in the upcoming slides, it will kind of always start with this kind of syntax where we're going to import the MPI module, initialize an MPI job, and then define the COM rank and size. So after that, what we're going to do in this case is we have a variable sendBuff, and it needs to be initialized on all processors. So remember, when you're running MPI, a copy of this program will run on all processors simultaneously, and sendBuff needs to be defined on all the processors. So we'll initially define it to be nothing, and then on the rank 0 processor, we're going to define a list. In this case, the list is just going to go from 1 to size. So if we're running on 2 processors, this is just going to be a list 1, 2. If we run it on 3 processors, this will be a list 1, 2, 3. And then we're going to multiply that by 100. And we'll print out what the original array looks like. And then using this uppercase scatter, passing in sendBuff, it will automatically partition it into equal parts and then send that to all processors where it will be received in this receiveBuff variable, and then that is printed to the screen. So again, the argument structure here is what we're sending, the type of data we can expect to be received. In this case, it's just integers, the COM, and the root processor from which we are doing the scatter operation. So if we save this code in a file, scatter1.jl, then we could run this on the command line using the project-aware version of MPI.exe that we can install with Julia. So we'll run that. Number of processors in this case is 2, calling the Julia executable and then passing in the argument that is the file name, which again contains this code up here. And so when this runs, you'll see that this array is created on the rank 0 processor, and then this call to scatter distributes equally, right? And so in this case, there are 2 elements in the array, and we're running this on 2 processors. So each of those elements are then spread out or passed along to receiveBuff, which is then printed to the screen here. So if I change this and run it on 3 processors, you can see what happens. So again, now that we're running on 3 processors, we get the array 100, 200, 300 on the rank 0, and then that's equally distributed out to all of the other processors individually, right? So just like that. So next we're going to look at scatter exclamation point. So the convention in Julia always is a function with an exclamation point does some type of in-place operation. So in this case, it's quite, the initial code is going to be the same. importing the module and starting the MPI job and defining column rank and size. And again, initializing send buff to nothing. But this time we're also going to initialize a receive buff to be a vector, an empty vector of length size, right? So if we run this on 2 processors, this will be of size 2, and if we run it on 4 processors, it will be the size 4. So it's just a vector, and again, it's defined. Remember, a copy of this runs on every processor at the same time. So initially, every processor has a variable send buff equal to nothing, and receive buff is equal to a vector, an empty vector of size, right? So then on the rank 0 processor, we're going to basically just create a random array of floats. This would be a 2-dimensional array that's has size number of rows and size number of columns. So again, if this is run on 2 processors, size will be equal to 2. So this will be a 2 by 2 array or matrix, you can think of it. We're going to print off the original array, and then we're going to call this scatter with the exclamation point. And again, the send buff followed by the receive buff, a communicator and root. So in this case, we've already defined what receive buff. So what is sent will be automatically imported into the receive buff, and you'll see it there when we print it to the screen. Okay. So in this case, if we save this code to a file scatter2.jl, then we can run this command. And again, the original array on the rank 0 processor is this 2 by 2 matrix. And then you can see what is passed along, right? So in this case, rank 0 gets this array and rank 1 gets this array. Now, one thing to notice is because Julia, like Fortran, has a column first memory ordering. So even though you might expect this to pass along the first 2 entries of the array here along the rows, the way this array resides in memory is actually column first. So in memory, it has this first value here, followed by this value, followed by this value, followed by this value. So when we pass those along, it passes the columns, right? So if you notice, this array here is the columns of the original array, right? This is the columns, the first column of the original array is passed. So, we can, again, run this on 3 processors if we'd like. And now we have a 3 by 3 matrix originally, and we're passing each column to the individual processors like this through the scatter command. So finally, there's this Scatterv exclamation point, which allows us, it takes some additional syntax, but it allows us to send non-uniform size or send non-uniform partitions to all the processors. So in this case, this code is only meant to be run on 2 processors. It's not a very good MPI program, but it will demonstrate the idea. So again, initial part of the code is the same. We're going to define the send buff everywhere to be nothing. On rank 0, we're going to define a receive buffer that is of size -1. And on rank 1, we're going to define a receive buff that is of size +1. And otherwise, the send buffer will be, again, a 2 by 2 array. Again, this will only work on 2 processors the way it is written. And that's because you have these additional arguments that you have to send to the Scatterv command, where you have the links. So in this case, for the 2 processor case, this will be size -1, so that's 1, and size +1, that's 3. And then the offsets, right? So these are going to be where in the array you're going to start the send command from. So for the first array, for the first processor, we're going to start at the beginning of the array, so no offset, 0 offset, and we're going to send size minus 1 entries, right? So in this case, that's 1. And then the next offset will start at the first entry of the array, 1, or the 1 index of the array, and then have a size plus 1 length, right? So in this case, 3, right? So again, I think the best way to show this is just to show what happens when it runs. But the Scatterv syntax, then we have to construct this so-called BV buffer, which contains the send buffer, the links, the offsets, and the data type, and then that will be received into the receive buffer, the communicator, and the root processor, and we're going to print out the results. So again, if we save this to a file Scatterv3.jl and we run it, again, this will only work on 2 processors as it's written, so it's not a great MPI program. Good MPI programs will be parallel consistent, meaning you could run them on any number of processors and get a consistent result. But just the way that this offset thing works, then this is what we have. So we have originally a 2x2 array, and we're only going to send 1 entry, right? Size minus 1. We're only going to send 1 entry to the rank 0 processor, and we're going to send size plus 1 or 3 entries on the rank 1 processor, and you see that those are the ones that are received. So again, in the order will be, again, down the columns. So this first entry goes to the rank 0 processor, followed by the second entry in the column, and then the first entry in the second column, and the second entry in the second column, right? So that's just, again, because of the way that the memory is stored in Julia as a column first ordering, okay? So moving on from scatter, we have the kind of opposite operation, the gather command. So in this case, we're going to collect results from all processes into a list. So again, same initial code. SendBuff is initialized as nothing everywhere, and then on rank 0, we're going to create a list that just goes from 1 to size. So again, if this is on 2 processors, this is just 1, 2, and we're going to multiply by 100, and we're going to then scatter that out to all the processors. Just like we showed before, receiving it as a vector v, and then what we're going to do is square that vector, and then we're going to gather the results back on the rank 0 processor, right? So we're going to gather the result, this is the squared value of v, back to the rank 0 processor and print the result here. And so again, if we run this on 2 processors, you'll see that the original array is 100, 200, that is then scattered. So rank 0 gets 100, rank 1 gets 200, and then they're both squared on those processors and then gathered back to the rank 0 processor, right? So 100 squared is 10,000, 200 squared is 40,000. This will work as well if we run it on, say, 4 processors. Just like that, right? And again, we can't control the order in which things print to the screen, so you see things are a little bit out of order here, but nevertheless, everything works properly. It is parallel consistent. So I'm not going to go through all the variants, but they're very similar to the scatter command. So there's the gather exclamation point, which will allow us to receive into a receive buffer in place. The gather v command, which will allow us to receive ununiform entries from the different processors. And there's also the all gather variants as well. And so in this case, gather just gathers the results to a single rank. In all gather, the results would be gathered on each individual rank. So each individual rank in the network would also contain the results of the gather command. And so and then they have their exclamation point and v exclamation point variants as well. So now we're going to broadcast, right? So broadcast is where we take a single copy of something on every rank and then distribute it to distribute a copy of that same item to all of the ranks, right? Broadcast it. So again, same initialization code. Send buffer is initialized to nothing, On rank 0, the send buff is going to be a string. It's just going to be a message that says hello from rank 0. And we're going to broadcast that to all ranks. And then on each individual rank, we will print out the result, right? And so again, if we save this code to a file called broadcast.jl and we run it, and then you get these individual messages. So each processor received this message, hello from rank 0. And again, we can run this on a different number of processors if we'd like. And there it is for the 3 processor case. So that's broadcast. There's also the exclamation point version, which would also include a receive buffer where the receive buffer is already allocated on the processor, and then the message is received into that buffer in place. Okay, so in reduce was kind of already described on the first command, on the first slide, at least for the addition case, and that's the case we're going to demonstrate here. So again, same initialization code. Now this time, we're going to create on each processor a vector. So in this case, so again, it's just a vector that goes from 1 to size. So if it's 2 processors, this will just be 1, 2. We're going to print that to the screen on each individual processor, and then we'll do a reduction operation where we're going to do an element-wise addition of each vector, right? And it's addition because we're specifying the operator here. And again, then on rank 0, we're going to print out what is received, sum the total of those to get the total sum, and print it out. So if we save that code to a file reduce1.jl and we run it, you can see the results here, right? So originally on rank 0, we have an array 1, 2. Also on rank 1, we have an array 1, 2. And then what we're doing is doing a reduction operation. So it'll be 1 plus 1 is stored in 2, and 2 plus 2 is stored in 4. And then we call this total sum, which sums up this array. 2 plus 4 is 6, right? And so we can run this on, say, 4 processors. So now we have lists on each individual processor that go from 1 to 4, and we're going to sum up along the columns in the reduction operation. That gives us this, and then we can sum the total of those again to get 40. Now the thing with this reduce is that we can define, in this case we're just using the regular plus operator, but we can define our own operation for the reduction as well. So in this next example, what we're going to do is, and we've seen this in other Julia code where we define this struct to be a point. So the point has 2 fields, x and y, and then we define or overload the plus operator so that the addition of 2 points means adding the 2 fields together, right? So if I have a point A and a point B, each of those have x and y coordinates, then A plus B results in a point where the 2 x coordinates are added together and the 2 y coordinates are added together. So then, same thing in this case. Instead of just creating a vector on each processor, we're going to create a point where the entries of the point have are just rank. So on processor 0, this will just be 0.00. On processor 1, this will be 0.11, and so on. We're going to print it to the screen. We're going to do the reduction operation, and again, it looks like we're doing the same thing because we have a plus here, but this plus, because Julia is going to be type aware when it does the plus, it's going to use multiple dispatch to call this version of plus up here, and we'll get our correct reduction. So if we save this code to file reduce2.jl and then we run it on, say, 3 processors, then this is the result we get. And again, you can't control printing the screen, but on rank 0 we have a 0.00. On rank 1 we have a 0.11, and on rank 2 we have a 0.22. And so then the new point after the reduction operation is the summation of these, right? So we're just going to sum up the x components, 1 plus 2 plus 0, and 1 plus 2 plus 0, and we get the correct result there, right? And again, this would work if we ran it on, say, 4 processors. And that's what we get. All right, so we're just summing up the columns. 1, 3, 0, 2 is 6, and likewise for y. So there's also an exclamation point version of reduce, where the reduction would be saved into an already allocated receive buffer, as well as the all versions, all reduce and all reduce exclamation point, where instead of the reduction operation being only done on the rank 0 or a single rank processor, it would be done on all processors, right? So you would have a version or a copy of this point on every processor after the all reduced operation. So that's an overview of the collective communication operations in MPI.jl.